Let me just quickly recap what we did yesterday. So what we essentially did was we were able to derive the Navier-Stokes equation from very general principles. And what we also discussed about the Navier-Stokes equation were ideas of symmetries and conservation laws, global conservation laws, just so that we know where we stand, and the role of nonlinearity. This played a role in the distribution of kinetic energy across scales. And then we sort of moved into the other aspect, the two aspects that we will need for the rest of the class lectures to understand what turbulence does or brings to the table. We also sort of looked at essentially nonlinear deterministic systems. And we showed the ideas of dissipative dynamics, attractors, etc., and the fact that you essentially have a positive Lyapunov exponent. So this is just a quick sort of recap of things that we did in our lectures yesterday, and this sort of sets in some stage, in some sense, the stage to actually now dive into turbulence, which will be somewhere in this limit. Okay, so before I do that, your tutor Ritik, who's a tougher guy than I am, he's asked me to ask you all to bring laptops, those of you have, for the tutorials today, because he will actually make you all work. All right, so good luck in the afternoon session. All right, so what we saw in the previous, in the class yesterday is, I'll just write down the Navier-Stokes equation once again. And let's add, for good measure, some forcing, right? Because we often talked about stationarity without being very precise about it. But now, this makes more sense, because now you have a forcing mechanism, which I call F. You have a dissipative mechanism. So in principle, it would be a bit like your chaotic water wheel, where you had an injection of water and a leakage of water, right? And what we saw from the global conservation laws in the last class was that the rate of change of energy, kinetic energy, was something given by this factor, which is essentially something like the curl of U whole squared. And if I have this additional term, I will have which supplies me additional energy. So as we discussed in the previous class, if you actually take a time series of the kinetic energy from a wind tunnel measurement, or you're able to fly a balloon up in the sky or deep in the ocean, what you might end up getting, and if you had instruments to measure the kinetic energy, you would end up getting a signal which would be something which is fluctuating, all right? However, if I take large enough time windows, I may not have drawn this very well. Certainly, I haven't drawn this very well. But if I take large enough time windows and I calculate the average energy, what you will find is that the average energy over reasonable time windows is constant. All right. So essentially, what you'll have is that there is probably some energy level E0, and the rest of it is fluctuating like crazy around E0. What will concern us are these fluctuations. This is where the sort of fun in this problem lies. But if you were to do it, so then in an average sense, if I were to take time window averages, you will see that in steady state, on average, you will have 2 nu omega equal to the stuff that you're injecting. All right? Excuse me. And this is something that we had labeled as epsilon in the previous class. All right? So necessarily over long time windows, what you will have are realizations where you sort of tend to average things out. So you take average of this equation, which comes directly from the Navier-Stokes, but now I've put in a little forcing term, which really doesn't, it helps in manipulations, but it really is not that central to the ideas that we are going to develop. And what you will end up having is this relationship. So before more formal definitions of what is about to follow, this whole picture has a very nice sort of phenomenological idea behind it, and I'm going to sketch that out. And certainly tomorrow, I'll also be using this picture quite a bit and make modifications to it. But essentially what this says is that you are essentially injecting energy at some large scale L that I don't care about. Some large scale, it's suppose, if this is my fluid, it could be the scale at which I'm waving my hands, or if it's a sort of wind tunnel or a sort of washing machine, actually experiments are done in washing machines, it would be the sort of scale at which these propellers are stirring stuff. If it's your cup of coffee, it would be the sort of extent at which you're taking your spoon and stirring things around. And this whole picture loosely translates to the following picture. You have some large scale L where energy is being injected. You certainly have, as we saw in the previous class, you certainly have some small scales where these blobs are now really small. Remember, viscosity is coupled to the Laplacian of U, so that is really something which acts at very small scales. And those scales, I will just, through set notation, I will call that scale eta. And this is where the energy is getting lost through heat or whatever, through the molecular viscosity. And in between, what we'll have is a whole range of scales. I'll call these length scales as R, where there is a constant flux of energy. Well, there's a flux of energy we haven't established if it's constant, which I will call as pi. All right. So the mental picture that we have, which comes from these equations, is the fact that you have an F term, which is acting at very large scales. You have a dissipative term, which is multiplying the Laplacian of U. So it's something which is acting at very small scales. And from the filtering thing that we were doing yesterday, we have the nonlinearity, which is essentially transporting some energy from these scales all the way down to the viscous scale for viscosity to take over. All right. So that's roughly the sort of picture that we have in mind. And what we are trying to do is trying to see whether this picture corresponds to some calculations that we can do from the equations themselves. So one of the first things that come out from this is something I had mentioned in passing yesterday, is the fact that we are dealing with a multi-scale problem. The fact that you certainly have these large scales and these small scales and stuff in between. Again, to set notation, let me just write it down. This would be called the dissipative scale. This will be called, historically, the inertial scale. All right. So now if we are in steady state, which is where we began, it is likely, I mean, that seems to be the only obvious choice, at least in an average sense, that the stuff that you inject, the stuff that you get rid of for things to be stationary so that there are no piling ups of energy at some length scale, etc., you should expect that I will be equal to pi, which will be equal to epsilon. You would expect this sort of relationship to hold. All right. And that's just a restatement of the fact that we are in we are in statistically steady states, and things are defined in some sense in terms of averages. And the fact that we actually have these things suggests that we certainly have some lengths, the L length scale, much larger than the length scale over which this cascade is happening. This is a simplified picture, of course, and that in high Reynolds number turbulence, this constraint does seem to work. So what's the claim? What are we going to prove with this? So the claim that we are going to make is that the physics of this inertial range, and that's the physics that we'll worry about in the next 3 days, the physics of this inertial range is going to be universal, and it will not really depend on whether you're performing your experiments with air, water, or honey, as long as you have cranked up, God knows how, the Reynolds number to be large enough so that there is enough of scale separation. All right, otherwise the nonlinear term will just drop out, and then you'll have something which is essentially going to be essentially going to be a local diffusion equation. So what do experiments tell us? At the end of the day, we'll try to make a theory which will connect to what we see in experiments. Well, they tell us many things, but we'll concern ourselves with just 2 things for the moment. So the first thing experiments have told us, and these are experiments which were carried out in wind tunnel, which were carried out in the oceans, etc. What they told us was the following, that if you take a length scale R, which is in this sort of inertial range, or a length scale R, which essentially is far away from the boundaries, is far away from the dissipative mechanism, and then you calculate the velocity. Let's not worry about vectors for the moment. Velocity difference between 2 points which are separated by R. Then experiments tell us, I should be a little careful, that this animal scales as R to the power 2/3. Right? That's the only thing that experiments have informed us, and this is sort of, in the decades of the 70s. There is a nice corollary to this, and this is something which Ritik will cover also in the tutorial, the fact that this second order quantity scales as R to the power 2/3 means that if I were to calculate in Fourier space the distribution of kinetic energy across Fourier modes, the density of kinetic energy across Fourier modes, this is absolutely consistent with a scaling of the spectral energy density as k minus 5/3. When one sort of people sort of give colloquium on turbulence, that's probably one of the first things they show you, that that the energy is distributed across wave numbers as k to the power minus 5/3. It's a natural and simple consequence of Fourier transforms, and we'll do a bit of this in the tutorial with Ritik. So the first thing that we know is from experiments is that relation holds. Now we'll try and see this relation, why this is indeed correct in a slightly more precise manner, but let me sort of nevertheless make the following statement is this particular sort of relation can also be seen completely dimensionally, all right? So I'll let you all figure this out as we go along, but when I try and sort of derive this a little bit, you'll see that it will just take you half a minute to see that this is absolutely dimensional as long as your velocity is length over time and distance is length, etc. This follows. The other interesting observation that people sort of gathered from experiments and more so from full numerical simulations of the Navier-Stokes equation was that epsilon, that dissipation term, in the limit of viscosity going to 0 is a constant. Now, there is a little more caveat to the statement. You have to ensure that all the other parameters in your experiments are held constant, and there's a way and a unique way in which you can sort of start reducing the viscosity. But the fact that with those caveats, which we don't need to worry so much about unless we are doing real mathematics, with those caveats, there's this surprising result, which goes by the name of dissipative anomaly, that epsilon tends to a non-vanishing finite number as viscosity goes to zero. This is quite surprising for all of us. That's because you know Newton's laws of motion. If I start rolling this chalk and assuming there's no gradient, the chalk stops at some point because of friction, right? Assuming I'm not doing anything else. And so if I were to reduce the friction and take it all the way to zero, assuming there are no other things happening, this chalk will go on forever. Friction and viscosity are somewhat similar in spirit, but here we find a situation where even when viscosity goes to zero, you have finite dissipation. So this is the sort of, when we were looking at global conservation laws yesterday, I did mention that, it seems reasonable for us, but we should treat it with some caution, and we will look at how to see this. So the question really is for us, how do we explain these two laws starting from the Navier-Stokes equation? Now, as you can guess, the reason I've drawn those nice pictures is that there are problems to explain this starting from the Navier-Stokes equation. Now, the main problems that arise when you sort of use the Navier-Stokes equation is, firstly, you're dealing with a nonlinear equation. And in principle, you do not have an exact solution for u of x. So if I give you suitable initial conditions, I really don't know a way how to solve this equation. Right. The second problem is, you can well say as physics students, that what happens if I just look at the Euler equation where there is no viscous term and then add viscosity perturbatively. After all, I'm interested in solutions of turbulence where viscosity is necessarily a small number. Can't I just do perturbation theory? Now, the problem with perturbation theory for this is, well, several. But the main problem is that after 200 and whatever 70 odd years since Euler wrote down his equations without that viscous term, we don't know enough about solutions of the Euler equation. It's something that people work on. It's an immensely challenging problem. We don't know well enough to actually use perturbation theory on solutions that we don't completely understand. All right, so there's a problem there. So the third one is the following. At the end of the day, essentially, I'm looking at moments, right? So in principle, and all of you have sort of done StatMech, and Sanjib was going through this also in his first lecture in a bit, you might think about actually calculating moments, right? So there's a function, you calculate moments, you generate moments, etc. There again, there's a problem, and the problem really comes from the nonlinearity. So you will see that if you want to calculate the nth moment, you need to figure out what the n plus 1th moment is. This is a standard closure problem, and this will be the subject of my last lecture on Friday, where I'll deal with how to sort of kind of rectify this problem a little bit. Okay, so left with little or no choice, let's first try to understand things much more phenomenologically. So what is this? So let's first look at this problem. All right. So they should come here. So what have experiments told us? Experiments have told us in a turbulent flow, take 2 points labeled by crosses at a separation small r. And then if you calculate the square and average it over ensembles or over time because it's in stationary state, and then if you were to plot this versus r, For convenience, I'll take some logs because power laws show up as straight lines in log-log plots, as Akshit was explaining to you all. What we end up getting is an initial R-squared behavior, which really comes from Taylor expansion, assuming that the functions are analytic and can be expanded. And then you have this regime if you have been playing around with the data that Ritik sent you, you'll see that things are not as nice as what I'm sketching on the blackboard. And you have a number 2/3 here. All right. Now, as I said, let's first sort of convince ourselves that 2/3 will be the number. What you can do is, using the ideas that we sketched and the energy balance, you know that delta U squared, let's say, can only depend on the flux because that's the only thing which is being transported across these length scales. So to the power alpha, and it can also depend on the scale, as we can see, r to the power beta. Now it's a sort of trivial exercise for you by just looking at power counting that you will see that alpha is 2/3 and beta is 2/3. Which essentially satisfies what you will see experimentally, right? So we'll see that there is departure from this, but assuming that you are dealing with self-similar functions, assuming that there is exact scale invariance, assuming that this picture holds, which repeated experiments have shown it to be correct. So people have measured these things in a variety of experiments and simulations, and they found this r to the power 2/3 robust. And this result has been also verified from actual data, and just naive experiments sort of tell you that this is indeed the case. So let's sort of. By the way, a lot of the next couple of days will be on various expansions of this. So if you're in doubt as to what is the function that I'm calculating, good time to clarify that. All right? Yes, Abhishek. Yes, yes. So this would be d dt that comes from what's erased now, which came from the balance of energy that we're looking at. In principle, one can do it in 2D, and you'll get it. Yeah. Okay, so since you mentioned 2D, as I mentioned yesterday, is not on my list of things, but since Abhishek mentioned, let me sort of refer to you to this fantastic review paper by Crichton and Montgomery. So I'll just take half a second. I'll just take half a second to answer Abhishek's question. So in 2D, the results will be a little different. That's because the conserved quantity is not just energy. And so if you're dealing with conservation law, there's energy conservation, which will give you exactly this, but there's also conservation of other quantities, which lead to even dimensionally different scaling results. Right? Okay. So now you can ask the following question is, what happens if I'm not just satisfied by taking the square of this, but I take any arbitrary power? And I have an exponent zeta p, which is now dependent on the power that I'm taking. All right. If things were nice and simple, you can sort of, using similar dimensional arguments, you can convince yourself that beta turns out to be p over 3. This is at the heart of Kolmogorov's world. That these are known as equal time exponents in literature. In case you want to Google, just Google with equal time exponents in turbulence. So these exponents, Kolmogorov suggested, are just simple scaling laws, and these exponents scale as p over 3. So those of you who are sort of more mathematically inclined, and we'll come to this issue in a little bit, you immediately see when we were doing scaling groups in the Navier-Stokes equation yesterday, We made a point that the scaling exponent h can be infinitely many as long as viscosity is small or going to 0. So this sort of argument, at least for the moment, fixes my exponent h to be 1/3, and that's really the Kolmogorov picture. There is one additional remark I would like to make before developing a more systematic theory, and that remark is the following. In particular, for p equal to 3, this exponent turns out to be 1. 3 by 3 is equal to 1. All right. This, by the way, is an exact result that is long and tedious to prove. Uriel Fischer's book has perhaps the best proof of this result. This actually follows from the Navier-Stokes. As I mentioned, the Navier-Stokes, okay, that's erased. As I mentioned, the Navier-Stokes equation has a closure problem, but however, when you calculate the third order analog of what we have written here, so place p equal to 3, there are certain miraculous cancellations, and eventually you get zeta 3 equal to 1. Right? So the bottom line of this is that whatever exotic theory that you want to build of turbulence, where all of this is disobeyed, as long as that turbulence follows Navier-Stokes, if you come up with a zeta 3 which is not equal to 1, we have to talk about it very seriously. Otherwise, I'm very happy with other exotic theories, which gives me whatever zeta p you want, but this constraint has to be satisfied. Okay, so let's go for a more, conscious of the time, let's just go for a more systematic derivation of this. Where, so this pi will have dimensions of kinetic energy by time. They're all in per unit mass. Per unit area, per unit mass. There's no per unit area. So this is the flux of energy. So it's dE dt. So exactly. So this would be, this guy will be meter square per second square. That's kinetic energy by time. It's the rate of flow of kinetic energy. This guy will be meter. And so you see there's a meter cube over second cube, which is the same as velocity to the power 1/3. Okay, so that's the definition. Because you remember the Navier-Stokes equation as a del del T of u, so I'm multiplying, hitting it with u. So I have del del T of u squared. Right. So another way to think about it, sorry, just give me a sec. Yeah, yeah, yeah. It's the same. So another way to think about it, Abhishek, is you can think about, so remember I had drawn these little eddies at length scale r. You can think about the rate at which the kinetic energy on such an eddy jumps over to the next one. So there's a local deformation time, TR. There's a total kinetic energy V squared. So the rate of deformation of that energy carrying eddy will just be energy divided by time. We'll use some of these ideas. But just stupidly, this is just the rate at which energy is transferring downstream. All right. So let's make it slightly more systematic. By the end of tomorrow, we'll make it fully systematic. And on Thursday, we will do it in a more stat-mech appealing way in terms of coarse-grained hydrodynamics. But today, let's just follow today and tomorrow. So what we will follow is loosely, K stands for Kolmogorov, 41 stands for the year 1941, when he had this series of 3 papers. And what he did in this series of 3 papers was lay down in modern language the following hypothesis. And we'll see whether everything follows from the hypothesis. So the first hypothesis would be that if I'm in the large Reynolds number limit, then all possible symmetries, which we discussed yesterday, of the NS stands for Navier-Stokes, are restored. and away from boundaries. All right. So what it means is that if, as we had, if we define velocity increments delta u in the following fashion, homogeneity and isotropy will tell us that if we replace this x with some large x, following way, that this will be the same as taking a translation with some vector x. Okay. So it really doesn't matter if in my pair of points, what it really means is if I take the initial point here, 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 or here. All right. The second hypothesis of Kolmogorov, which will be very useful for us, again in the same sort of setting of Reynolds going to infinity, etc., is flows are self-similar. Now, this is a strong assumption, and later theories sort of try to understand this, but let's say experiments and direct numerical simulations puts this in sharp focus, which is something that we learn today. So essentially, it means that you have a Hölder exponent, which is real, and a unique one, h. So remember here, we figured out that h was 1/3, right? Just because what experiments told us. And then if I combine it with this idea, then it turns out that h is equal to 1/3. All right. And to derive everything else in a remarkably sort of prescient way, this is really a hypothesis in Kolmogorov's world. But as I said, this seems to be experimentally borne out to be true, right? And I mean, we will not really be doing it, but those of you interested, there's a very nice set of articles between Landau and Kolmogorov, sort of serious debate on whether this is indeed correct and how does one sort of modify the theory that I'm going to present with such modifications. All right. So within these set of hypotheses, if you impose scale invariance, so you sort of, what we did the previous day, if you sort of assume this is a simple exercise. If you plug it into what we are calculating here, you will again find that h will be 1/3. All right, so to end this first part, and then we go through this in some detail. So what do we sort of summarize this as? Just so that the key facts are sort of crystal clear. It shows, so what Kolmogorov sort of said is that flows are self-similar. What that means is there is a scale invariance. So increments will scale as r to the power h. All right. And so if we use that argument, that's what we did. Actually, I did it the other way around because of a question that was asked. So if we play that game here, we ended up seeing that beta is, this exponent here is p/3 drawn from, and so p equal to 1 gives me the Hölder exponent, which is 1/3, right? And you can try and play this game and come to the same conclusions in various different ways. So to summarize, under assumptions of homogeneity, and isotropy, of course, in a statistical sense. Then constant epsilon and self-similarity. We get H 1/3 zeta p over 3 and completely from a different approach, which is starting with the Navier-Stokes equation, you get really an exact result, which is zeta 3 is equal to 1. This zeta 3 equal to 1, by the way, goes by the name of Karman-Monin-Haworth theorem. It's tedious, so I'm not going to do it. It may not be particularly useful or illuminating. So let's see how we built up this again from another perspective, right? And the reason I'm building this up from different perspectives is because tomorrow we will see how all of this eventually leads to what is known as a multifractal prescription of flows, the fact that things have exotic objects, things that you kind of saw in the Lorentz model yesterday. Okay. So you remember the phenomenological model that I had initiated? I should have mentioned this is due to the model, not the calculations per se, are due to Richardson in 1926. So we are really celebrating 100 years of, and this name you would have seen in context of dispersion, etc., where probably he's more universally known. So in that picture, I'll just draw a short sketch of it here, but not a big way. Remember, this was the cascade picture that we had in mind, the miniature version. So let's define notations. So for R, where R is in this range, we can define a typical velocity scale. There are several ways to define this typical velocity scale. It really doesn't matter how you do it. But if you want to sort of have some sort of an intuition for it, you can define the velocity scale as some VR, which for dimensional reasons would be okay. So in that picture that I have, you are at the nth generation. So this picture is really talking about some big matriarch or patriarch in the family of turbulence, and they're spawning generations of smaller and smaller eddies, typically happens. And then eventually these eddies become very small and dissipation takes over and they die, sadly. All right, so this would be the typical velocity scale at scale R. We can also define some sort of RMS velocity at the larger scale. Again, none of these definitions are going to be very precise, but you would expect that the RMS velocity at large scales where the fluctuations are not going to be that dominant, it's a meaningful sort of reference scale to have. Okay. So this would also allow us to have some sort of a local turnover time scale. So I'm using this word because yesterday at lunch I realized some of you are from an engineering background. So this is what in conventional fluid dynamics, you would call as an eddy turnover timescale or something of that sort. And this would merely be the timescale associated with the length scale. So just, naively this thing. And this would also tell me what Abhishek was asking, the timescale of transfer of kinetic energy from the nth generation to the n+1th generation. All right. So essentially, if you do that, I'll erase this. All that you need to remember is the self-similarity bit. The others, I think we have sort of stressed over. So this would essentially mean that if I look at the transfer of energy over scale R, it would really be the amount of energy I have at that scale that I can define because I've sort of defined the local velocity times velocity scale. So it will just be some VR squared. I don't really worry about constants over tau R, which if I put all of this back together, essentially gives me VR cube. That's the loose sort of phenomenology on which we have started building things. And this is what, it's good to sort of understand this well at this stage, because this is something that we'll distort as we go along in the next few days, in the couple of days. All right. So now we know from experiments, we know from what we did in the first part of today's lecture, that this will be equal to epsilon. This is what we began with. Remember, we had that boxed equation which followed from Navier-Stokes, that under statistically stationary condition, you have the injection balanced by dissipation, but then you needed something to take the energy from the large scales to the small scales, and we call that guy pi. Stationarity would demand that the number of chocolates I give to Abhishek, what he passes down to the rows behind, and let's assume the guys in the last bench are viscosity and will eat up all the chocolates. So there should be a constancy in the flux of chocolates which are going down the stream. So this must be equal to epsilon, and then lo and behold, you immediately see from here, and this gives a nicer way to think about the scaling exponent. H is 1/3, which follows just from this sort of simple phenomenological model. Okay. The interesting thing will happen, as we shall see tomorrow, is when we try to put in a little bit more realism in this model, and what would the consequences of that be. All right. So I should also tell you, tell this for people who sort of look at particle problems, motion of particles in complex medium, etc. You can certainly use these arguments to construct ideas of dispersion, etc., for particles in complex medium, right? You start with two particles close by, you can think about their relative velocity in this language, and then you can see how explosively these sort of particles separate. So again, a good reference would be in the school by Sanjib and Abhishek. I think last year, the year before, Jeremy Beck had a set of lectures on spontaneous stochasticity, etc., which all picks up from dispersion ideas. So strongly sort of recommend, if you're interested, to look into that. All right. Now, in particular, I can take my R going to go all the way to L, or I can take my R to go all the way to eta. Right? I mean, this is a free scale, so I can sort of push this up to go to L, or I can push this down to go to eta. The reason that becomes very useful is if I'm comparing with experiments, as you will see, it will help me to define reference scales. So if I do that, then when R goes all the way to L, what you end up having is defined as V0 or VL? V0 cube. Right. Excellent. And you'll see immediately why I need this, right? Because I can then equate this to what I have there, and I can write the velocity at scale r in terms of the large scale velocity, which I can somewhat control in a numerical simulation by how I'm forcing, in an experiment by, what's my typical sort of grid size or fan blades, etc. So just to finish notations, I can now take the opposite point of view. When r goes to eta, I know that at these small, there are several ways to think about this, but since you all have done diffusion, I know at scales less than eta, the only thing which is happening, the only time scales in the problem are just viscous diffusion. So I can write things here as just a viscous diffusion time scale, which in principle must, have I used tau or t? Probably with my handwriting, it doesn't matter if I've used tau or t, they all look the same. So I can calculate this at eta, and I can equate the two time scales. And that gives me something very nice. I won't go through the calculations because we are running late as usual. When you do this, you actually come up with a very precise prescription of what the small scale inner flow is. Not surprisingly, it depends on viscosity. So this stands to reason. The larger your viscosity is, this scale will just slide up here. So it might go from, let's say, 1 millimeter to 1 centimeter. For sense of numbers, for example, in atmospheric flows, or you can just plug in these numbers from Wikipedia for various fluids, you will see that these are of the order of, well, ranging between millimeter and centimeter, let's say, between as you go from atmosphere to the oceans. All right, so we have actually managed to calculate what the dissipative scale in this problem is. So everywhere where I have this, now I actually have a number for eta, which depends on what is there in my system. Epsilon is set by the large scale flow, and so everything ties in neatly. You can sort of go over similar arguments, and you can calculate the velocity associated with the scale eta. We already did it actually, you can calculate the time scale associated with the scale eta, do all of that, and you have also a nice way to think about the scale. Remember, my Reynolds number was some velocity into some length divided by viscosity. And we had discussed yesterday that Reynolds number is dependent on scale. It depends on which length you're choosing, which velocity scale you're choosing. If you put in this guy, etc., you will see that Reynolds at scale eta is 1, and it goes further down. Yeah. So this also gives you some sort of hand-waving justification of what we were discussing yesterday, that at viscosity-dominated scales, nonlinearity doesn't really play a role. Right. Excuse me. And there's one result more that I will just show you, which is the following, which is using all these things, you can put them all together. I won't go through the intermediate steps, but if you put them all together, you will find that this goes as. So the scale separation between the large and the small scales as Reynolds to the power 3/4, which essentially means, after all, we'll look at things in power laws, right? And so if you were to come up with a result from experiments, numerics, or theory, and you want to calculate scaling exponents, you want this scale separation to be as large as possible, right? Because then, then when you make log-log plots of something where you want to see the scaling behavior, you don't want this regime to be too small, right? Otherwise, the old Neumann story, you can fit anything if it's very small, all right? So you need to make this inertial range large, which essentially means you need to get the ratio of the large scale by the Kolmogorov scale to be very large, and you see that ratio is Reynolds to the power 3/4. It grows sublinearly with Reynolds. It's pathetic, but that is what it is. So bottom line is, numerical simulations or experiments are pretty hard. So even if you crank up Reynolds number by a factor of 2, you won't really gain much in trying to get good, well-averaged data. You can just about get away with anything, and no one will believe us, okay? So bottom line, if you have friends who do turbulence simulations or experiments, have some sympathy for them and treat them with respect and honor and sympathy. Okay, great. So that's the problem that people have. So this is good. We had experimental results which gave us a certain scaling exponent, 2/3, consistent with k minus 5/3. We used Kolmogorov's sort of hypothesis, which in hindsight, a lot of it is right, some of it is partially right, which again gave you the same Hölder exponent h equal to 1/3. Then what we did was we used this sort of cascade picture, which was appealing from the way we set up global conservation laws from the Navier-Stokes equation, and we took a different approach and we found out the same h equal to 1/3 exponent. Furthermore, it gave us a nice way in which we could fix the different length scales and the velocity scales and the Reynolds number, etc., which enter our game. So now let's look at what is it that is happening really in experiments. So we ended the business by saying delta u of r to the power p scales as r to the power p third, which means zeta p is equal to p by 3, zeta 3 is equal to 1. So people actually went ahead and did experiments. I had just told you what experiments told us about the second order structure function, that zeta 2 is 2/3. But then people said, well, might as well measure all the values of p and see whether things fit in a straight line. So you calculate this, you take log-log plots of this animal versus r, log. Let's say this is p equal to 1, this is p equal to 2, which we said would go as r to the power 2/3. This is p equal to 3, which we said has to go as r, p equal to 4, which Kolmogorov tells us goes as 4/3, so on and so forth, right? But you need not believe Kolmogorov, right? You might as well calculate from fits, from experimental data. And when people did that, they found the following. Kolmogorov would say that these exponents fall on this straight line with a slope p by 3. Etc. But when people actually made measurements, p equal to 0, they found this to be slightly larger than 1. Whether it matters or not, we'll see. But within all statistical error bars, it's, larger than 1/3 within all statistical error bars. This, which we claimed to be 2/3, also seems slightly larger than 2/3. You can ask, how does it matter? It matters because it's really prodding that little bad wolf called scale invariance. If things were really self-similar, you wouldn't have this departure, or if things were really Gaussian. Then, thank God, the experiments picked up zeta 3 to be 1, bang on. And then as you went further, we saw this departure from the Kolmogorov world becoming more and more pronounced. All right? And this departure is significant. It's not in the same universality class of when you were asked to calculate value of G in high school from a simple pendulum, and you were not sure which value you should get, 9.81 or something else. Okay, this is really significant. Repeated experiments, repeated simulations over the years have all pointed to the fact that the Kolmogorov theory is not exact, right? I'm refraining from writing the word not exact, but that's what I mean. All right, so the interpretation of all of this is, let me go back to white chalk. The interpretation of all of this is A, there is no unique, and the other part, which we won't go through a lot, but this was done in your sort of partly in your lectures last week, is that we know that these are moments and they should be related to the PDF of delta U, right? You know expectation, x to the power p is equal to x to the power p integral of p of x dx. You'll have done that. So the fact that you do not have this simple scaling, which is true in a lot of classical physics, also seem to suggest that if you were not to calculate the moments, but you were actually to calculate distributions of these delta u's, you would find them to have very, very big tails. And probably on Friday at the end, when I'll just talk about interesting problems, you will see that some of this can be related to large deviation principle, Cramer's functions, etc. So this and the fact that PDF of all these measurables are non-Gaussian seems to be the real problem in turbulence. Okay. So in particular, PDF being non-Gaussian, let's say I calculate the PDF of delta U. I think Ritik sort of showed some of these plots yesterday, and I hope his plots looked a little bit like what I'm about to sketch. Otherwise, it'll be a bit of a disaster. Seems to have these big fat tails, which are far from Gaussian. It might have a Gaussian core, which is not entirely clear from the way I've drawn it. But let's assume it has a Gaussian core, but it has real big fat tails. So what big fat tails means, apart from cosmetics, is the fact that you have finite probability of very large events, right? And this is something is how you should interpret distributions. Forget all other jargon, but it really means that you're looking at something where there are rare events, because this is going to be whatever the x-axis value is, it's a rare event. But if you compare with this, let's say if I look at the value here, Gaussian would give me a probability somewhere here, but the fact that I have a big fat tail gives me a much larger probability of observing these rare events. And this sort of leads to something that has bugged several people working in this field for several years, especially those from applied maths and stat mech sort of community. This is something which goes by the name of intermittency. All right. Essentially, intermittency deals with the fact that signals are on/off. I'll explain what I mean by this. And you all are all very familiar with this, especially during COVID, with all those Zoom meetings where half the time you were saying, can you hear me? Can you not hear me? Right? So that's an example of something which is certainly intermittent. Or several years ago, when we were younger, telephones used to work similarly. All right. So a quick example would be, for example, if you calculated the dissipation rate that I said was constant on averaging, but if you just stuck a sort of, a measuring device at one point and you were able to measure how much kinetic energy is dissipated as heat at that point and did a time series, you would find things which are something quiet, with no perceptible pattern. So this epsilon seems to have this very rugged, very jagged behavior where there are long periods, or whatever long means, where nothing happens, then there are things which happen, then nothing happens, and there are things which happen. We will try to see how these two sort of pictures are essentially compatible. But before that, let me sort of probably, I think it's okay if I go a little slowly. Okay, I think this we've beaten to death, so I can remove this first quickly, because I'll make a digression now on theory of random functions and intermittency, a small digression. Otherwise, I don't want to do it on turbulence without showing a simple textbook examples. But you're clear on what the problem we face, right? We could have gone back home if our experiments showed that these exponents all fell on the Kolmogorov prediction. Where will we get the noise?
In the equations.
No, but in the system, okay, so there is a possibility that you might be thinking of something like thermal noise. Now, thermal noise typically will act at scales which are A. You might discuss a little bit whether thermal noise will be relevant at the scales at which we've coarse-grained the hydrodynamics. So we have coarse-grained it at scales. Eta is still quite a few orders of magnitude larger than the mean free path. Secondly, so let's see whether thermal noise really matters. Secondly, we know for a fact that that thermal noise, even if you include it, will be acting at very small scales. Whereas I'm looking at the inertial range. And third, ignoring theory for a bit, is that those orange points that I've drawn there, these orange points coincide with several different experiments where there's no modeling involved and simulations of Navier-Stokes. So to the extent that my experimental exponents and simulations of the Navier-Stokes gives me exactly the same exponents, it does seem reasonable to assume that the Navier-Stokes equation is a good description. So I think that's something that is perhaps, at small scales, I agree with you. But those are not the scales that one is looking at. Small scales, one might have to worry about other things. Okay. So I'm taking this example because this was done last week. All right. So let's look at Brownian motion as an example of a random function. So is Brownian motion scale invariant? Is it self-similar? So, you know, it's self-similar. Right? You all had lectures on Brownian motion last week, right? So Brownian motion is a nice example of a random function which is self-similar and scale invariant. One way to think about it is if you look at the velocity versus time of a Brownian function, and so you have something like this. And now if you were, I mean, that's an intuitive way to think about it, but this was done much more precisely. And Ritik, in one of his tutorials, if we have the time, will sort of destroy elements of Brownian motion to make them compatible with what we are doing. You would find that the signal looks roughly the same. All right, it really doesn't depend on the enlargement window that you're looking at. So this is an example of a function which is self-similar. So let me give another example of a random function which is not self-similar. This random function you can generate, actually you can generate it trivially using your calculators. You build up a Cantor set. You know how to make a Cantor set, all of you? Yes, no, maybe? Okay, no. So essentially you take the line and you chop off 1/3 parts of it sequentially. So in the beginning you keep divide that line into 3 parts, scoop out the middle, then you have 2 little disconnected lines, but there's still dimension 1 left. Then on each of those lines you play this game iteratively, and then you eventually have a set of discrete points which are actually not on any integer dimensions. All right. So now, instead of scooping out those lines, if you sort of add them, so it's like a Cantor set, but where you keep on adding mass, what you end up getting is a function, let's say as a function of time, some function t, which looks like this, right? So this is known as a devil's staircase. It's an example of a random function It's an example of a random function which is certainly not self-similar. The reason it's not self-similar, unlike your Brownian motion that I sketched there, is because if I take my window here and look at the function, I'll just get a straight line. It will not look anything like this staircase, right? Whereas if I slide this window and I put it here, then perhaps it starts to again look like the original function that we had. So it really matters in that sort of devil's staircase kind of function exactly where I'm placing my window, and that's sort of an intuitive way to sort of think about functions which are self-similar or not self-similar. All right. So quantitatively, what we can do is the following. So let's consider a stationary function v of t of this one or the two types that I've drawn there. And then I can think about its Fourier transform in some real domain. All right. So let's use the filtering technique that we introduced in the previous class. Again, keep in mind, those are the two versions of a self-similar and a non-self-similar function that we have. What I can do is I can use, so I'm defining it again because yesterday was a long time ago. Okay, so I have a cutoff scale, capital omega. So now, a working definition of what intermittency will be is if I calculate what's known as flatness, so I take my angular brackets and the other brackets are also quite self-similar. They're actually very similar, not even self-similar. All right. So if I calculate this guy, then for functions which are intermittent, this animal will grow with omega. You can go back and redo some of the things that Abhishek and Sanjib were doing for your Brownian motion, and you will see that this is a condition that will not be met there. All right. However, here you will see, or I'll make this example slightly more illustrative, you will see that this certainly works. So one way to sort of by hand construct, well, you got what we did, right? I just sort of passed the function through a filter where there's a cutoff. So it's as if I'm taking off my glasses, and so I can only see things up to a certain scale. And I've taken the fourth power, done the average divided by the second power, average, then square. And now, does it depend on what my cutoff frequency was? If it does, that means the function is intermittent. So everything depends on the scale at which you look at. And so scale invariance is lost. All right. Okay, very good. So now you can play the same game, but let's do it. Let's take the signal on which we are going to do. So let's say this is my signal. And then I make it bursty by construction. So what I'm going to do is I'm going to copy the same signal, but I'm going to take the eraser and remove parts of it. So that will be like the epsilon versus time plot that I showed you, right? There were periods where there was nothing, and then there were periods where there was a lot of activity. So let's construct another signal, which I get from here. So I make a copy of this as faithfully as I can. But the way I've sketched it, there are parts of this signal which are multi-valued. That is just my own inability to draw things correctly. That's not intentional. They're all single-valued functions for the moment. All right. What I've constructed from here to here, what I've done is I've chopped off 1 minus omega of the total time, which I've chopped off. Okay. Let's say if I take this to be 0.5, so roughly half of the signal, I've just taken my duster and I've wiped off clean to replicate the epsilon versus time kind of picture I've drawn. So this, to the notion that we had at an intuitive level, this is certainly a signal which is intermittent. So you can, of course, calculate the flatness of this. This is easy to do. And you can immediately see that what I'm going to do is, this is SV gamma. And you can convince yourself that this animal goes as 1 over gamma, simply because V gamma to the power 4 will just be gamma V to the power 4. V squared gamma on average will just go as gamma, the fraction that's not there, and V squared of the original signal. So this again shows you by construction that an on-off signal will have a flatness which depends on scale. Okay. And so a few final remarks. So if your thing is Gaussian, you will see that the flatness for a Gaussian signal will have a unique value, which is equal to 3. F is equal to 3. It doesn't depend on any scale, and this, by definition, will be non-intermittent. Right? Second, if you have a self-similar function, this will also be non-intermittent. You can actually calculate this using exactly this. So replace capital omega with a lambda omega and redo the same calculation, and you will see that essentially we will see that V lambda omega will be lambda minus H. And you can use this game and you will see lambda V omega to the power 4 and V squared taking the square of it. Both will pick up factors of lambda minus 4H, which in the ratios will cancel. And so, self-similar functions cannot be intermittent. This is going to be true for your standard Brownian motion. So, if experiments and numerics seems to suggest that Kolmogorov laws or the sort of the picture of universal scale invariance in turbulence is not true, then what's going on here? So what's going on here is the following. You can ask the question, is turbulence self-similar or intermittent? It can't be both. All right. So at the really small scales, we're going to measure energy dissipation. The intermittent characteristic of turbulence is really apparent. You have epsilon versus time, and it really looked like what I constructed by hand, that there are quiet periods and not quiet periods. However, in the inertial range, which is much more of interest for certain kinds of physics, this is less obvious. And it sort of only shows up that it's not perhaps really scale invariant with a unique exponent a la Kolmogorov in actual measurements of these theta p's, right? So by the way, I should, again, there is a very nice paper by Frisch and Rudolf Morph, in 1981, where, through several nice examples and mathematical structures, the issue of small-scale intermittency, connections of intermittency with self-similar functions, theory of random functions, all of that is nicely worked out. So it's a paper which sort of goes beyond turbulence, and I think it would be very nice for most of you. Okay. So before we go back to actually deriving these things, let me make following remarks. So maybe in the interest of time, I will probably not derive these results right now, but state it, unless while stating I'm lost myself. Okay. So back to this picture. All right. So you can come up with some so-called exact results on intermittency. All right. So these would be exact to the extent that, as we shall see, they will give us certain bounds on how these zeta p's will behave. And the reason we will need these exact results is to keep ourselves honest when we, again, go back to first phenomenology to try and understand how we can depart from Kolmogorov and get this sort of shape of these exponents, all right? So whatever we do should follow the exact results that I'm going to now either derive or state, depending on how hungry all of us are, okay? So one constraint which I'm not going to derive, as I said, is this. I'll just leave it hanging there without talking about it anymore. So to derive these exact results, we make the following assumptions. One is, in the Reynolds going to infinity limit, R becomes small, or what we have is some constant, which I don't care. This is just restatement of the fact that there is self-similarity at some level. We know what those exponents look like. Those exponents look essentially what I've drawn there. So we'll assume that there is some sort of self-similarity. This limit is compatible with the Reynolds going to infinity limit, because if you remember in what we derive for the lower bound on R, in the Reynolds going to infinity limit, that is also getting pushed out to 0. Remember, it went as viscosity cube over epsilon to the power 1/4. All right. Second assumption, I'll write here. 1. That's 2. For large but finite number, scaling still holds, so that thing still holds, as long as 1 some power law in Reynolds, right? This assumption can be sort of, worked out in a backward way in using ideas that we were kind of implicit when deriving the Navier-Stokes equation and incompressibility. All right. So with these, let's derive one constraint. Let's say constraint 1. So maybe I'm not going to derive this actually because we are running quite late. So I'll just write the constraint. Let me get the end of my derivation. So for P2, if you take any 3 numbers, P2, P1, P2, and P3, then All you need to do is basically use Hölder's inequality for random functions. So this is something in real analysis. So you take any random functions, take it to some mth power, and you'll, with powers m1, m2, m3, and they follow a certain inequality. And what you will see is, under that assumption, you will find P3 minus P1 Now, if you think about this relation, which I didn't derive, you can derive it by taking logs on the Hölder inequality for any three random functions. What you immediately see is that this constraint, which is an exact constraint on the different exponents, suggests that the shape of this curve has to be of this form. So from tomorrow, when we try to derive a theory to get this shape, we shouldn't end up with a theory which gives me these exponents which are going in any way different. It has to be concave, all right? So that's an exact result that we have to satisfy. And the second constraint, and this is a constraint that many of us, when we do numerics, we end up violating, and then we remember, oh, this constraint existed, so my numerical results must be absolute garbage. All right. So the second constraint is the following. Maybe this I can prove, because this is, the steps are smaller. So let some u0 be the largest maximum velocity in my flow. Magnitude, I don't really care. And so this will imply that in magnitude, the same delta UR that we began about an hour ago, this must be bounded by U0, right? If U0 is the largest, then let's say I'm calculating the velocity difference between me and Abhishek. If both of us are at U0, that's the maximum, then the velocity difference will at max be 2U0, right? And nothing more. So now I can calculate the 2p plus 2th power. So I can calculate I just take the square. All right. I take the 2pth power, and that follows trivially from the first statement. And now I know, where do I know? I know from here, right? So I can replace my left-hand side and the right-hand side with what I have there, where these A2Ps are constant, universal or not. We will not worry too much about it. And what I end up having, just by cancellation, is an extra V0 squared, which comes from this term. Then I have A2P plus 2 divided by A2P. Then I have R over L minus Okay, everyone with me? Or all of you are quite tired? All right, so I end up with this relationship just by assuming that I have a maximum U0 in my field. So that curly brackets is just a shorthand way to say that there's a max velocity amplitude. All right. Now suppose this term dominated over zeta 2p. So suppose, so if that was the case, then this little combination will be what? This little combination will give me a positive number, right? 4 minus 3, 2 minus 1.7, something like that, correct? But we know from the assumption there r going to 0, or r over L becoming small, we know from that assumption that this guy will become very small. So something very small raised to the power negative something will certainly blow up, right? So if this condition holds, that would mean that this goes all the way to infinity, which we know is not possible. That's because everything is bounded. And so the second constraint, let me write it down here. So this is, let's say, constraint 1. So the second constraint is zeta 2p less than equal to is valid. Okay. All right. Again, as you see from the data that we have from turbulence, that second constraint also seems to be satisfied. That second constraint, by the way, certainly allows a scenario where at large P, these might end up being constants. I'm not saying they will be, but I'm saying that the second constraint, which really is a restatement of the finiteness of kinetic energy or the finiteness of the velocity field, also allows us to think about scenarios or think about theories where this happens. So if from your experiments, or more likely from your numerical data, you end up seeing this saturation, that certainly is not going to violate the two constraints that we have discussed. Okay? So in the next 40 minutes, what we will discuss, that's tomorrow, what we will discuss is first, before we adapt this sort of phenomenological model, before I return to the phenomenological model to try and make corrections, make things fractal, etc., while keeping those mathematical identities intact, try to see if I can bend Kolmogorov's law to my will and fit this data. But before that, tomorrow I will do a simpler model of turbulence, not field of turbulence, but a simple 1D nonlinear system called the Berger's equation, where I will see that you can prove all of this exactly. So it's a good inspiration and marginally relevant to turbulence. But I think it's good to see exact results a little bit more before we again, so I'll sort of go back and forth between exact results and soft phenomenology. Okay, thank you.